Hey everyone, welcome to our third part when we go through and try to figure out how these ionic compounds tend to work. And so a simpler way to balance ionic compounds is really what the focus of this lesson is about. We spent the first two videos really going through and talking about how you could draw Bohr diagrams and then use Bohr diagrams as a way of coming up with ionic compounds. But in this video, we're going to start to get away from the Bohr diagrams and use what we can learn about the periodic table and see if that can help us write it a little bit simpler. So we'll use a couple of examples as a means of kind of learning through the process. So again, I encourage you to pause the video, copy down the examples, try the notes, and see just if you can follow along, if you're understanding kind of what's going on. So we're going to go through an example. So we're going to use calcium and fluorine. So step one is to write the symbols, and we always place the metal first. Now from our previous unit, our metal group is always to the left of the staircase, and the staircase is basically this thicker black line that starts by surrounding boron, which is atomic number 5, and kind of goes diagonally down through silicon, arsenic, tellurium, and astenine. And so everything to the left of there is considered a metal. Everything to the right of there considered a non-metal. So we always put our metal group first. So in this case, calcium would come first, fluorine would come second. So start off, list our elements. Step 2 says write the ionic charge above each symbol to indicate the stable ion that each element forms. So we need to figure out what the ionic charge is of calcium without drawing these Bohr diagrams. We also need to do the same thing with fluorine without drawing Bohr diagrams. We've done fluorine quite a bit, and we know that fluorine has 7 electrons in that outside shell. If we were to do Bohr diagrams for calcium, we would see that calcium has 2 electrons in its outside shell. And so calcium, if it has 2 electrons in its outside shell, is going to want to get rid of the 2 electrons that it has, and it's going to take a 2+ charge. Fluorine is going to want to accept a single electron to fill its outside shell because it has 7 already in its valence shell, and so that would give it its 8. So fluorine is going to have a 1- charge because it's going to pick up an extra electron. So how can we use the table to our advantage to kind of see what these would be like? So the periodic table that you have is going to be a great reference for this stuff. So if you were to find these 2 elements, and I've just kind of copied them on the sides here, if you were to look at these 2 elements and specifically look at certain spots in them, right here and right here. So calcium, it tells us right in the element box, has a 2+ charge. That location on the periodic table for every element is actually its ionic charge. So fluorine, it's telling us, has a 1- charge with it. Remember, 1- is saying it's gaining an electron because electrons are negative, whereas a 2+ charge is saying it's getting rid of 2 electrons, and so it's carrying 2 extra protons overall. So we can look at any element on your periodic table, and I encourage you to pause the video and actually take a look at your periodic table and just kind of look around, and you'll see that there are numbers written basically 2 spots below the atomic number in the 3rd line. That's the ionic charge of that specific element, or the most common ion charge that's there. So once you find those charges, place them on the top of the table, top of each atom. So calcium, I'm going to put the 2+ on the top, and fluorine, I'm going to put the 1- on the top. And then the next thing is to cross the 2 charges and then to get rid of the signs. So what do I mean by that? So cross your 2 charges. So I'm going to take the 2+, I'm going to cross it and put it where the F is. And then we take the 1- and I'm going to cross it and put it where the 1 is. So notice here that when I write out the numbers, what's happening is there is no sign getting carried over in either of those scenarios. So the plus and the minus sign just go away, and I'm just left with the numerical value that's there. Now, number 4, step 4, ignore the 1s, combine the terms together, and reduce them if you can. So ignoring the 1s, okay, so there's calcium had 1 next to it, so I'm going to get rid of that, which is the reason why when you look at the answer, there's no 1 there. And fluorine has a 2, so I'm going to put the 2 there. So I have CaF2. It takes 2 fluorines to balance out this 1 calcium. Number 5, step 5, to name the compound, name the metal first, followed by the nonmetal, and then change the ending of the nonmetal from normally an INE, change it to an IDE. So whenever we change things to "ide" at the end, we're indicating that it's an ionic compound, or maybe not necessarily an ionic compound, but that it's a compound, that the atom itself is changing into a compound. So we would say the one up on the top, if you want to try to take a guess on what it is, we'd say the metal first to name it, so calcium, and then we'd get rid of the "ine" at the end for fluorine, and we would change it to IDE, so calcium fluoride. So calcium fluoride would be the name for our ionic compound. So this crossing system works really well for us to come up with the charges. Now, what is really happening here? What's going on? When we cross, effectively what we're doing is we're balancing this out the same way you would do if you had like fractions, for instance. We know calcium has a 2+ charge, so I'm going to see if this thing can balance out to be 0. So calcium has a 2+ charge, and I have one of them. I'm going to add that together with fluorine that we know has a 1- charge, but I have 2 of them. So if I have 1 times 2, I have 2+ altogether, and then I've got 2 times -1, so I have 2- altogether, and when I add 2 positives and 2 negatives, I get a net effect of 0. Right? They cancel each other out. 2 minus 2 gives us 0. So when we cross, really what we're doing is we're setting up kind of like a common number that will give us 0. And so this crossing trick works really well, because really we're just kind of trying to see if the overall protons cancel out the overall electrons. Okay, the overall charge of the positive atom cancels out the overall charge of the negative atom. So let's take a look at our table here and see if we can't kind of summarize some of these points together. So what we just saw was that in our last example was that calcium had a 2+ charge. And really, in fact, if you were to look at your periodic table with me as we're kind of going through this, really every element in this list, if I were to look at beryllium and we look at the top corner here, do you see how beryllium in its outside shell has 2 electrons? It's going to have a 2+ charge. And if you look at your periodic table, you'll see in the box that beryllium indeed has 2+ written down in the most common ion spot. In fact, magnesium, calcium, strontium, barium, and radium all have 2 electrons in that outside shell. And so really group 2 is known because they have ions with the charge 2+. If I look at group 1 and start going through the list, lithium has 1 electron in its outside shell, so it's going to have a 1+ charge. And then I could go through the same list with sodium, potassium, rubidium, and they all have 1 electron in their outside shell. So group 1, our alkali metals, carry a 1+ charge. And I could keep going on in this list as we count across the table. The number of valence electrons in the outside shell just go 1 electron for alkali metals, 2 electrons for alkali earth metals, and then we're going to skip our transition metals. We'll come back to those in a second. So 1, 2, 3 electrons in our group 3, 4 electrons in group 4, 5 electrons in group 5, 6, 7, and 8. And so if I were to look at any of them, nitrogen, it's in group 5, so nitrogen has 1, 2, 3, 4, and 5 in its outside shell. The charges of them run really nice because they just go 1+, 2+, 3+. Then when we get to carbon, remember carbon has 4, so that's kind of even. Carbon is balanced, so it actually doesn't want to gain or lose electrons to make an ionic compound. So this group 4 actually gets skipped. It's already halfway there. And then after that with nitrogen, we start to go the other way. So if you look at nitrogen, look at the common ion, you'll see 3-, and then go to oxygen, 2-, fluorine, 1-, and then our noble gases are stable. Because all of our noble gases on this side all have full shells already, so they're already balanced. So overall on your chart, it just goes +1, +2, +3, even, and then nitrogen would be -3, -2 for oxygen, -1 for fluorine, and then even again. Because when I look at these noble gases, they're already full in their outside shell. So there's a neat little trick just in terms of taking a look at your metals to nonmetals and understanding kind of what the charges are on them. Your nonmetals are always going to want to gain electrons. Your metals are always going to want to accept electrons. And as you move left to right across the table, it goes from wanting or giving away more electrons to wanting to gain electrons back in to stabilize their Bohr diagram. So let's take a look to make sure, for instance, that it's balanced. It's very important to understand that our total positive charge has to equal our total negative charge. Similar to what we did when I was adding them together in our last slide, right down here and going through and seeing that we had, you know, 1 atom of 2+ and 2 atoms of 1-, and so it canceled out to give us 0. Our total positive charge has to equal our total negative charge all the time in order for these things to balance out. So there's 2 here. I want for you to take a look at your table, see if you can identify the charges, see if you can come up with the compounds, follow the steps, and just see if you can balance them out and then name them. So pause the video, give it a try, and come back when you're ready. Alright, so if we took a look at the first one, I'm just going to come up with the charges first and just write them above the elements, because that's what that first or second step kind of went through. So aluminum has a 3+ charge, chlorine has a 1- charge, beryllium has a 2+ charge, oxygen has a 2- charge. Next thing, I'm going to cross my charges over to the other side. So really I have Al1Cl3. I'm going to omit the 1 and write out what's left over, AlCl3. Now, it says reduce if possible for step 4. I can't reduce this any further. I have a 1 and a 3. It doesn't reduce. So I would call this aluminum. And instead of chlorine, we change it to chloride with that IDE ending. In my next example, I cross my charges, and I have Be2O2. So now, once I've crossed them, I'm going to see I have no 1s. Can I reduce this? And the answer is yes in this case, because I have a 2 in each case. So how can I make that smaller? Well, it'd be the same way if you had a fraction and you had to reduce the fraction down. Basically, you have 2 in each spot. I could divide each one by 2, and I could make it smaller. So I could really turn this into Be1O1 if I just divided by 2 for each of these elements. And the reason why I couldn't do it in the other one is because if I divided by any number other than 1, it's going to give me a decimal, and I can't have half atoms. They have to come into whole numbers. So now if I get rid of the 1s, really I have BeO as a final formula. And so what do I have here? I have beryllium. And then instead of saying oxygen, I've got instead of saying oxygen here, I've got oxide. So oxide for a final with the IDE ending. Okay, so going through and naming them just for a little bit of extra practice. So we'll come back for the final video, for video 4, and we'll cover transition metals and see what they look like.